this is Saritha, working as assistant professor in the Department of ECE, Institute of Aeronautical Engineering. Today's session, I am going to explain about example problems based on Hoffman code. So, in this Hoffman code, what are the basic blocks here? Source. Source is nothing but our input signal. Here, AK is nothing but gray levels. So, here, encoder, with the use of encoder, it converts whatever the gray level is there. With the use of encoder, it converts into binary form. Here, compression between this, after encoding and decoding, between these two, we are going to compress the data. So compression can be achieved by encoding AK, and here the output is AK. AK is nothing but we are representing with gray levels. Here encoder, we are in this we are having, when we go for Hoffman code, we need to consider code, code word and code word length. Code word length. So in this, code means code we are representing in the form of symbols or letters. So in each word, how many symbols we are using, that is nothing but code word. Code word length means when we are going to represent a gray level, how many number of bits we are using to represent that particular gray level. Here, there is a one-to-one correspondence between source symbol and code words. Here, optimal code, so minimizes code word length per source symbol. So here this is nothing but average length coding technique. So Hoffman code is a average length code, variable length coding techniques. This variable length coding techniques, when we go for represents a gray level, for example, gray level 1, 2, 3, like this. Here, fixed length means each and every gray level, we need to represent with fixed number of bits. But when we go for variable length code, each gray level we are representing with different bits. For example, I am representing the gray level 1, I am using only 1 bit. And to represent a gray level 2, we are using 2 bits. So this is nothing but variable length code. So in this, what are the steps involved in our Hoffman code? First, sort probabilities per symbol. And next, combine lowest two probabilities. So what are the probabilities are there? First, here sort probabilities per symbol. Here, whatever the word, suppose one word is there, in that word, how many number of symbols are there? Each symbol, how many times it occurs. So find out the probability of occurrence in that word and combine the lowest two probability values. All the probability values write in a descending order and add lowest two probability values. Repeat step 2 until only two probabilities. Here, consider one example. Here. A2, A6 for example, A1, A1. So here the probability value for A1, here it is 0.4. One example, for example, A1, A2, A3, A4. Here the probability value for A1 is 0.4, A2 is 0.2, A1 is 0.1, A4 is 0.1. So write in a descending order. So A1, A2, A3, A4. So in this case, in these probabilities, first we need to consider here average assuming binary coding. So in this we are using total 6 symbols. we need a 3-bit code. For example, A1, A2, A3, A4, A5, A6. Here, each and every symbol. In this, we are using 6 symbols. Each and every symbol we are representing with 3 bits. We are representing with 3 bits. So here 3 bits means A1, 1, 0, 0. So for 2, 0, 0, 1, 0, 1, 0. Here 1, 0, 0. Here 1, 0, 1. So A1, A2, A3, A4, A5, A6. Here each and every symbol we are representing with fixed numbers. So 3 bits only. Then what is the formula? How to calculate the L average? L average equals to K equals to 1 to L minus 1. Here I of AK into P of AK. So I of AK is nothing but length of the, so how many now? Here I of AK is nothing but length of the code word. So number of bits we are using. Here number of bits we are using. And P of AK. P of AK is nothing but here in P of AK, probability of that particular value. Here for A1, here the, for example, consider one example. Here the probability value for A2 is 0.4 and A6 is 0.3 and A1, A4, A3, A1 is 0.1, A4 is 0.21, A3 is 0.06, here A2 is 0.04. So these are the values. Here in this case A2 is, A2, A6, A1, A5. So here A5 is 0.04. Here I of AK, here it is 3 only. So the probability P of AK. So here it is 0.4. Here how to calculate this one? 3 into 0.4 plus 0.3 plus 0.1 plus 0.1 plus 0.06 plus 0.04. Here 3 into 1. Here it is 3. So we are using 3 bits per symbol. 3 bits per symbol. This is for binary bit coding. L average. We are calculating average length assuming binary code. Here the probabilities, just consider one example here. A1. Here A1 is 0.1. A2. Here it is 0.4. A3 is 0.06 and A5 is 0.04 and A6 is 0.3. So this is for, in this case we are using binary bits are equal. The length of each and the representation of each and every symbol we are using 3 bits. Then I of AK is 3. P of AK is 3 into 0.1 plus 0.4 plus 0.06 plus 0.04 plus 0.3. So here add these all values, then we are getting 1. So 3 into 1, here it is 3 only. So this is for binary code. So when we go for Hoffman code in variable length code, here it is the probability value for A1, A2, A3, A4, A5, A6. So here the probability value for A4 is 0.4, A1 is 0.1, here A2 is 0.4, A1 is 0.1 and A5 is 0.04 and A3 is 0.06, A6 is 0.3 and A4 is 0.1, 0.1. So write these all values in descending order. Here A2 is 0.4, A6 is 0.3 and here A4 is 0.1, A1 is 0.1 and A3 is 0.06, A5 is 0.04. So first add these two. So here it is 0.1, 0, 1. Here 0.1, 0.1, 0.1, 0.3 and 0.4. Next add these two. Here 0, 1. Here the value is 0.2. Here it is 0.4, 0.3. These values 0.2, 0.1. Add these two. Here it is 0.3. Here 0.3. Here it is 0.4. Add these two. Here it is 0.6. And next step is 0.6 and 0.4. Here it is 0, 1. Here it is also 0, 1, 0, 1. So based on this Huffman code, the variable length code, so consider here for A2. For A2, here it is 0.4, here 1 only, this one. And for A6 here it is 0 and 0. For A4 1, here it is, add these two. Here it is 0.1, 0.06 plus 0.04. Here it is 0.1 and 0.1 is as it is 0.1, 0.1, 0.2 and here in this step 0.4 is as it is, 0.3 is as it is and here 0.2 we are placing here and 0.1 is here. So this and next here it is 0.3 and 0.3, 0.4. Here it is 0, 1. Add these two. Then here the final step is 0.6. This one is here 0.4, 0, 1, 0, 1, 0, 1. So based on this, find out the what is the length for A5. A5, how many number of bits we are using here? 1, 1. Again here 1 is here. Here it is also 1. This one is here 0 and 0. So like this find out for A3, A4 and A1. A1, A4, A1, A3. So here in this case L average. So here k equals to 1 to 6, I of ak, p of ak. Here the representation of 3 into 0.1 and for next 1 into 0.4, how many bits we are going to, here 0.4 here, how many number of bits are required for A2? Here it is 1 only, here it is 1. So then we are going to represent with 3 into 0.1, how many number of bits are we are getting here for A4, so A4 is, here it is 1 and 0.2 plus 0.1, 1, it is 0.3, 1, 1, 0. Here 1, 1, 0. For A4, here we are going to represent with 3 bits and for A1, 0, 0, 1, 1. 0, 0, 1, 1. For A1, 4 bits. For A3, 0, 1, 0, 1. And next, here it is 0, 1, 0, 1. 0, 1, 0, 1. And one more bit, here it is 6. Here it is also 0. So 0. For A3, we are going to represent with 5 bits. Here it is 4, 3, 2, 1. Here it is 4. So based on this, multiply with 3 into 0.1 plus 1 into 0.4 plus 5 into 0.06 plus 4 into 0.1 plus 5 into 0.04 plus 2 into 0.3, it equals to 2.2 bits per symbol. So 2.2 bits per symbol. Here for A3, 5. And what about A4, A5? Here A5, 1. Here it is 1, 0, 0 and 0.3, 0. Here it is also 5 bits. So here A2 representation with 1 bit, A6 is 2, A4 is 4, A1 is 4, A3 is 5 and A5 is 5. So multiply 1 into, here 1 is A2, 1 into 0.4 and 2 into 0.3, 4 into 0.1 and 4 into 0.1, 5 into 0.06 plus 5 into 0.04. Then how many number of bits we are using here? Total 2.2 bits per symbol. So when we go for binary coding, in this we are using 3 bits per symbol. But when we go for Huffman coding, 2.2 bits per symbol. So this is nothing but in a fixed length code. Here it is variable length code. And one more example here. Here one more example. Example is A 256 into 256. The image size is 256 into 256 pixel. Digital image has 8 distinct intensity levels. What is the minimum number of bits required to code this image in a lossless manner? So in this example, 8 gray levels can be coded, 8 gray levels. So we are representing here log to 8 equals to 3 bits per symbol. 3 bits per symbol. Here log 2, 3 we are writing in 8 we are writing in terms of 2 power 3. Then log 3 log 2 2 means here it is 1. Then 3 log 1 means here total term considered as a 1. Then how many bits we are getting? 3 bits per symbol. Here in this the image size. So the digital image size, here it is 256 into 256 into 3 bits per symbol. Then we are getting here 96,608 bits per symbol. So this is the one example. So in this example, the image size is 256 and the gray levels we are using are 8. Then log 2, 8. So here log 2, 2 power 3. Then 3 into 1, here it is 3 bits per pixel. This implies the number of bits required to code. And one more example here. In this example, compute the entropy of the image given by f of m comma n equals to, the image is 4 by 4. In this, total number of pixels. Here it is 16. Here it is 16. In this image, we are having the gray levels are 0, 1, 2, 3. 0, 1, 2, 3. Here, occurrence, how to calculate the occurrence of the gray level here. The gray levels, how to calculate the P of RK. In this image, 0 is in 5 times. Then the probability of 0, here it is 5 by 16, and the occurrence of 1, 1, 2, 3, 4. So here P of 1 equals to 4 by 16, and P of 2 equals to 1, 2, 3, 4, 5, 5 by 16, and P of 3 equals to 1, 2, 2 by 16, 2 by 16. So these are the probability values. So occurrences of probability of 0 is 5 by 16, 1 is 4 by 16, and 2 is 5 by 16, 3 is 2 by 16. So the probability of occurrence of 0, then P of 0 equals to 5 by 16. Here, probability of occurrence of gray level 0 is P of 0 is 5 by 16, and probability of occurrence of gray level 1 is P of 1, here it is 4 by 16, and probability of occurrence of gray level 2, here how many times it occurrence is 5 by 16, and 3 is 2 by 16. So how to calculate the entropy? So what is the formula for this entropy? H of S equals to K equals to 0 to L minus 1, Pk log 2 power 1 by, here step 2, computation of entropy. The formula to compute entropy is given by H equals to minus I equals to 1 to N Pi log to Pi bits per pixel. This is the formula for entropy. So in this entropy, what is the probability value here? So first one, 5 by 16 into log 2 5 by 16 plus 1 4 by here 5 by 16, and the next one is 1 by 4 log 2 1 by 16, and next 5 by 16 log 2 5 by 16, and 2 by 16 log 2 2 by 16 bits per symbol. Here H equals to 1.924 bits per symbol. So here entropy we are calculating H equals to I equals to 1 to N Pi log to Pi bits per pixel. So here we are representing with 4 by 16 means 1 by 4 log 2 1 by 4 plus 5 by 16 log 2 5 by 16 plus 2 by 16 log 2 2 by 16 bits per symbol. So here the entropy for this given problem, here it is 1.924 bits per symbol. And third example here, consider an image strip of size 100 into 100 as shown in figure. The image consists of 4 vertical strips. 1, 2, 3, 4. The gray levels of the strips from left to right, from left this end to this end, here 64, 32, 16 and 8. The corresponding widths of the strips are here the gray levels, here it is 64, here the gray level is 32, here it is 16 and 8. And strips are number of pixels we are using. The corresponding width of the strips are 40, 30, 20, 10 pixels. So for this strip image, compute the entropy in bits per pixel. So in this 64, 32, 16, 8 are the gray levels. In this we are using the pixels are 40, 30. With the gray level 64, we are using 40 pixels. With the gray level 32, 30 pixels. With the gray level 16, 20 pixels. With the gray level 10, with the gray level 8, we are using 10 pixels. Here, the strip size is 100. The strip size is 100 into 100. Here, in this case, the total number of pixels in the image is 100 into 100 equal to 10,000 pixels. The probability of occurrence of each gray level is computed in this given table. Here in this table, here the gray levels are 64, 32, 16, 8. So in this, how many number of pixels? 40 into 100. Here 30 pixels into 100. Here 20 pixels into 100. Here 10 pixels into 100. Here it is 4,000, 3,000, 2,000, 1,000. Then here the total number of pixels. Here it is 10,000. Then here 4,000 divided by 10,000 equal to 0.4. It is the probability of occurrence. And 3,000 by 10,000. Here it is 0.3. And 2,000 divided by 10,000. Here it is 0.2. And 1,000 divided by 10,000. Here it is 0.1. 0.1. Here the probability of occurrence of 64. Here it is 0.4. For 32, 0.3. And 16 for 0.2. And 8 is 0.1. Here, how to calculate the entropy. After computing the probability of occurrence of each gray level, the entropy is given by the formula. Entropy is given by the formula. Here it is H of S equals to summation I equals to 1 to n pi log 2 par 1 by pi bits per symbol. In this first the values are 0.4 log 2 1 by pi multiply here minus 1.32 and log 2 1 by 0.3 here minus 1.74 plus 0.2 minus 2.32 plus 0.1 into minus 3.32. Here it is 1.85 bits per pixel. 1.85 bits per pixel. So, in this image, the image size is 100 by 100. So, in this we are using total 10,000 pixels. 10,000 pixels. Here the gray levels are 64, 32 and 16, 8. Here number of pixels are 40. Here 30. With the gray level 16 the pixels are 20. Here it is 10. Here 100 into 100 into 100 into 100. We are getting 4,000 by 10,000. Here the probability value is 0.4. 3,000 by 10,000. Here the probability value is 0.3. And 2,000 by 10,000. Here the probability value is 0.2. And 1,000 by 10,000. Here the probability value is 0.1. And next example is consider an image strip of size 50 into 100. Shown in figure, the image consists of 5 vertical strips. The gray levels of the strips from left to right are, here it is 128 from left to right. Here it is 64, 32, 16 and 8. Here how many the width of the strips are? The width of the strips are, here it is 35, 30, 20, 10, 5. Here the width of the strip is 35, 30, 20, 10, 5. Here 35 into 50. Here 35 into 50, 30 into 50, 20 into 50. Here multiply the given width into 50 here. In this 128, here the gray levels are 128, width is 40, width is 35, 35 into 50, and for gray level 64, width is 30, 30 into 50, and here 32, 50 into 20, 1000, and for 16, 10, 10 into 50, 500, for 8, 5 into 50, 250, here 50 into 100. Here, the total number of pixels in the image is 50 into 100. Here it is 5000 pixels. Then the probability of occurrence of each gray level is computed as shown in this table. Here, the probability value is 1750 by 5000. Here, the probability is 0.35 with 128 gray level. And the next 1500 by 5000, here it is 0.3 for with the gray level 64, and 0.2 with gray level is here 32, and next 16, for 16 here it is 0.1, for 8 here it is 0.05, 0.05. So in this, the next step is the construction of the Hoffman tree, which is shown in figure. From the Hoffman tree, the following codes are obtained for different gray levels, which shown in this figure. Here it is 0.35 into, here log 2 1 by pk, then we are log 2 1 by pk here. Here minus 1.52 plus 0.3 into minus 1.74 and 0.2 into minus 2.32 plus 0.1 into minus 3.32 and 0.05 into minus 4.32. Then here the entropy of the Hoffman code, here it is 2.06 bits per symbol. Here, the probability value with the gray level 128, here 0.35, for 64 0.30, for 32 0.20, here for 16 0.10, for 8 0.05. So, for the Hoffman code, what is the first step? First, write the gray level value in descending order and add the lowest two probabilities. Repeat this step up to final here finally we get only two probabilities only. So 0.10, 0.05. Here it is 0, 1, 0.15 and 0.020, 0.20. And here 0, here 1. Add these two. 0.35. Here it is 0.30. Add these two. 0.35 plus 0.30. Here it is 0.65. 0.65. So here it is 0. Here it is 1. In this 0.05. Here 1. 1, 0, 0, and for 0.10, 0, 1, 0, 0, 0, 1, 0, 0. Next 0.20. Here it is 0, 0, 0. Next 0.30. 1, 0, 0.35. Here it is 1. Here it is 1. So, here how many code word length is 4? Here it is 4, 3, 2. Here it is 1. Here the average length is given by L bar equals to K equals to 0 to N minus 1 Pk Ik. So here 0.35 into 1, 0.30 into 2, 0.20 into 3. Here 0.20 we are having 3 and 0.10 is 4, 0.05 is 4. Here the probability value is decreased, then here length is increased. So the probability value is decreased, then the code word length is increased. Here 0.35, here number of bits we are using only 1. For 0.30, here it is 2. For 0.20, here it is 3. For 0.10, 4. 0.05, here it is 4. So here 1, 2, 3, 4, 4. So multiply here 0.35 into 1 plus 0.30 into 2 plus 0.20 into 3, 0.10 into 4 plus 0.05 into 4. Here it is. Now multiply these bits, we are getting 2.15 bits per symbol. So the efficiency of the Hoffman code, here it is. Efficiency we are writing eta equals to H of S by L bar 2.06 by 2.15. Here it is 95.81%. This is the efficiency for Hoffman code. So in this lossy compression and lossless compression, so the difference between lossy and lossless compression here, in this compression, here that permits reconstruction only approximation of the pixels and with the use of it is irreversible, and in lossless compression it is reversible and reduce the quality and do not reduce the quality. Here the data reduction is higher. In this lossless compression, data reduction is less, and here smaller resultant file is not small. Here resultant file is smaller than original one. So in lossless compression basically used for in video, lossless compression basically used for in text purpose. In lossy compression here we are using for multimedia and data. So up to here in Hoffman code, we are number of problems are solved. So in that only one thing, first step is write the probability values in descending order and add lowest two probability values. If probability value is increased, then probability value is high, so number of bits are reduced. So if probability value is high means the code word length is very less, so the usage of number of bits are reduced. If probability value is decreased, then usage of number of bits are increased. So this is the Hoffman code, and it is a variable length code and error free code. Next session I will continue with some more coding techniques in our compression, that is arithmetic coding. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.